Yeah, so I'll try to make it 44 minutes. If not, yeah, let's see how well I'm doing in my websites. Yeah, so uncertainty learning is of course kind of a big topic. So for me, it's not super easy to kind of unify things that I've done with my PhD into one topic. So this is a possible title I came up with. But more specifically, I'm going to talk about robustness in learning-based control, meaning their uncertainty kind of is on the system level, and how do we leverage uncertainty or account for uncertainty in our control design. But on the other hand, we can also use uncertainty in kind of a positive way, I would say, by leveraging uncertainty as for actively reducing uncertainty in order to need less robust methods. Okay. There's a significant lag. I guess I have. Oh. Is it? Oh wow. Okay, it takes a moment. I don't know if it's on my side. Okay, anyway, so just to quickly introduce myself, I think I've told all this just during lunch, but just maybe also from Toronto. So I've done my degree in electrical engineering and bachelor's in 2013 in Berlin, so in the east of Germany. I've then, during this time and also later, I've worked as a software engineer in a small consulting company in my hometown of Hamburg. I then got kind of the sort of field of e-commerce, building web shops, this kind of thing. So this got boring really fast, so I decided to go to university. This time I went to Lübeck, which is a small town in the Baltic, originally Hamburg, and I studied computer science there. Afterwards, I went for my master's thesis, the first part of my PhD, to the Max Planck Institute for Intelligent Systems in Stuttgart, and together with Sebastian there. And then when Sebastian became a professor in Aachen in 2020, most of our research group moved to Aachen, and I moved together with our research group. Yeah, so you see like a small map, and you see kind of I have been to the north, to the south, east, and west, but there's like a small part missing here in Germany. There's kind of the, yeah, but otherwise, no. Okay, so let's now talk the more interesting stuff, which is kind of research. So first of all, I will go through kind of my basic research interests that I've worked on during my PhD. I will then go into more detail into selection of two topics on this. Yeah, but first an overview. So the first topic I've been working on is kind of Bayesian optimization or controller tuning, and the point is depicted in this small sketch here. So the idea is that we have a closed loop system. There is a policy that is parameterized by example here X, and this parameterization of the policy influences the closed loop behaviors. So what we get by running this closed loop is we get some form of trajectory, and then can evaluate this trajectory and see how good our control is. And then the idea of Bayesian optimization or any other black box kind of policy search is that we kind of ignore all of this dynamic going on inside, and we basically directly build a map from X to the performance, and we just treat this as an optimization. So the nice thing about this is we can ignore all of the dynamics that's going on. The bad thing is we ignore all of that stuff. So, I mean, one obvious downside here is that we compressed kind of our rich trajectory information in a single scalar, and obviously we're going to lose a lot of information here. Yes, so this is not like a super novel idea. No, people are doing this, and also people associated with this lab. So what I've been looking at is mainly local optimization, meaning so usually Bayesian optimization is a global optimization framework. here I've focused more on local optimization, meaning I have controller, I have policy already, and instead of now exploring the whole search space for a better one, I just want to improve the current policy. And then I improve step by step. This is usually faster. I can tackle much higher dimension problems with this, but I will converge to it. And more recently, I've been looking at a lot of time variant optimization problems. Here, the idea is that, for example, my system changes over time, meaning also performance function changes over time. And I'm now in an online setting of the online optimization. We have a.
Sorry, it's just the audio is a lot of echo. It's hard to hear what you're saying.
Yeah, thanks so much. Which microphone are we using right now? Okay, let's try and see if this works. Please keep us updated. I was on the other side yesterday and I was quite I thought we have to work on our audio. Can you see? Yes. If you continue, Adam, just let us know in a minute or two.
Okay, sure, yeah. Sorry to interrupt.
Yeah, so the time varying problem is kind of a little bit it's a little bit different because it's usually an online optimization problem, meaning we really care at every time step how good we are doing. We don't want to randomly try stuff online, and also the exploration-exploitation trade-off becomes kind of more involved because between two time steps, if I change my policy parameters, there's now at least two causes of the change I observe. So either the closed loop behavior has changed because I changed the parameters, or because the system has changed. Disattaching this and still kind of keeping track of the optimum. Is what this part of the research is about.
And Adam, is it better, or should we use the laptop microphone?
It's a little better.
Is
it hard to try the other microphone, or is it
Maybe switch on your microphone.
My microphone is really bad.
Okay.
Sorry.
We'll stick with this. Thanks, though. Sorry.
I don't want to expose this.
Does it regret more the timing?
Yeah, but yeah, I think it's just not very much optimized. But if you turn around your MacBook,
Okay, so is this somehow improved? I mean, now there's still people moving around, but
Yeah, I think that sounds a bit better.
okay.
Thank you.
Okay, should I continue? Okay. So I'm going to talk about the local optimization part soon. So the second topic I worked on during my PhD is what I want to call probabilistic robust control. And here so this is a very different topic. It's much more control theory, and the idea is we have some form of noisy data that you see in your system, then you build some kind of system model from this, some sysid kind of things, but here the special thing is kind of that we are building probabilistic models, so Bayesian kind of models, and then we leverage these for robust control. So this kind of picture here should symbolize a little bit. So we have our A and B matrices of our linear system, and then instead of defining some bound uncertainty set, we have this probability distribution over possible systems. And here, usually the goal is to give some form of guarantees
on the closed loop behavior, given just the noise and data and usually the linear system assumptions. And then because we have these probabilistic models, our T's will be probabilistic. So the last topic that I've been working on a little bit during my PhD, but which I actually would like to spend some more time on working, is this idea of a safety measure. So I will not talk too much in here about this now, but maybe we can discuss later if you're interested. And here the idea is basically to quantify safety. So what does it mean to quantify safety? Safety for us, first of all, means not failing. This is kind of the definition of safety we have. So we have the state space of our system, and part of the state space is a failure state. So in this little example of our hover ship here, it has different heights. In this example, it's just a discrete system, but everything works also for continuous state and action spaces. And basically, failing here is crash. And then we're asking, okay, so the idea is this comes from viability theory, where part of the state space is the viability kernel if there exists a control action that will keep me from failing forever. So we can kind of define this kernel for the simple system. I'm not going to explain all of this, but basically the idea is that here part of our state space is safe. This is the green things. Part of it is just a failure state. And then there also exists kind of states in between where I have not yet failed, but failing is imminent. No? So imagine a Lego robot running, stumbles, it can do 1 or 2 more steps, but it will fail very soon. So the core idea here is that we map this viability kernel into the state action space. We get what we call a viable set. And then we just put a measure on the size of the set. And from this, we can basically give each state action pair a number, which kind of counts how big the set is there. And this then quantifies. One of the cool things about this is that it is really independent of any kind of reward function. Right? So this is just based on the definition of the failure state and given by the system dynamics. And all viable policies are necessarily inside the viable set. Meaning, once I know the viable set, I can learn without failing. I can relearn whatever task I need without ever failing, because I know which action will lead to fail. And I can even define kind of a level set on the measure to say I have policies that are safe with some margin. And one of the nice things of this paper here is, or what we show in the paper, which I have forgotten to reference, is that we can learn the safety measure on data. Okay. I took way too long for this, but yeah. So let's now move on to the 2 main topics of the talk. The first one is going to be local Bayesian optimization, and the second one is experience transfer for robust control. So black box optimization, the idea here is we abstract away our controller tuning problem or whatever problem we have into this black box that I have colored black. And the idea is that we really don't have a lot of information about this function. It's just that we can basically query it. And this can model like a wide range of topics. Just examples I've worked on is process optimization. So I have a big machine that produces, in this example, plastic parts. This machine has a lot of parameters, and depending on how I set the parameters, the parts will be produced faster or have better quality or whatever. And kind of this can be treated as a black box optimization problem. We have also done model selection in the context of dynamical systems and machine learning, where kind of the optimization problem is find a good model architecture for the machine learning problem, which is also like, where this kind of black box optimization problem often comes up in high parameter tuning for the machine learning. And then we do this policy search problem that I initially introduced. So what is a black box function for us? we don't have an expression of this function, right? We cannot calculate it, we really have to query it, we have to do an experiment, we have to train our model or do some reinforcement learning experiments in order to get the information. They're expensive to evaluate, meaning I want to be data efficient. So doing machine learning training problem, I don't want to do this millions of times. No, I want to do this a handful of times. Usually evaluations are noisy, which kind of makes optimization also much more difficult. Meaning if I run the same parameters again and again, I always get slightly different results. And critically, I don't get the root. Just by querying the spec box, I just get a function value. I do not get a derivative. So super popular strategy to solve these black box optimization problem is Bayesian optimization. I'm not going to introduce Bayesian optimization here just for the lack of time, and I guess most of you are familiar anyway. And I will directly skip this. No, not that. Okay, so the idea is here we are not, so we are doing this in a local way, and we kind of mix local optimization, Bayesian optimization, and the algorithm that we proposed we call weighted information Bayesian optimization, or GIBO shorts. So here the goal is we want to do fast local improvements, and we are restricted to noisy zero-order information from which we need to kind of learn the gradient and then do our updates. We want to tackle the high-dimensional search spaces, where a high-dimensional means kind of higher dimensional than what we normally do in GIBO. So GIBO works on dimension problems like maybe 20 parameters we can tune, but after that it really gets takes forever to even find kind of good solutions, or like not even optimal, but solutions that are not super bad. And we want to do this in a principled way. We want to have our own exploration exploitation trade-off that we have in Bayesian optimization in order to boost data efficiency. So it's called something with gradient, no? So I guess a spoiler, we are going to need the gradients. How do we get the gradients from zero-order informations? So we start by modeling our objective function as a Gaussian with the Gaussian process. So you can see here kind of sketch of a Gaussian process where our true unknown objective function is this black line, and the GP is this blue thing. The mean function is dark blue, and the GP also has some variance, which is here indicated in the slide. Okay, now one of the observations that we can make is that if we have such a GP model, we also get a predictive distribution over its derivative. Now, this is just a math to do, but once you write down this model, getting this is basically automatic. And because Gaussian processes are closed in a linear transformation, the predictive distribution over the derivative is again a Gaussian process, meaning you can compute this all in closed form. And what is even nicer about this is once we computed this we basically get for free. This is all nice to know, but very unexciting before adding some data. So let's get some intuition. Let's add some data points. So we now have a single zero-order like function evaluation that we put into our GP, and we look at what does the predictive distribution of the derivative. So we can see that now, just from this, we learn that the gradient somehow has to move up to this point. The gradient has to increase, and then it moves down again, so it has to decrease. Again, so this model kind of makes sense. It captures something we know about the gradient. However, we also see that we don't really get a reduction in variance. So we still don't know much about it, other than it decreases maybe, then it decreases again. But this is also not super surprising, since from one single evaluation, getting gradient information is hard. If we can put down like some kind of numerical differentiation, it's kind of impossible, no? This is also true in the GP framework. So if we add more data, we see also the variance of the gradient reducing. And what is kind of interesting to note maybe is that the variance behaves very differently in the original space versus the derivative space. Now, we see that the variance of the gradient is not basically small where we evaluate it, but it is smallest in between points, which again makes sense about what the derivatives are. Okay, so this is now what we will use in order to have a principal trade-off in learning things about the derivative from zero-order information. So in Bayesian optimization, we have what we call an acquisition function, where basically we score every possible point in our domain with how good it is, or what is the utility of knowing this point. And for GIBO, our algorithm, this acquisition function captures how much does the uncertainty get reduced at a specific point. So let's say my current policy parameters are here, and what I want to know is what is the gradient at this point. So I indicated kind of the size of the uncertainty as this line. And now the acquisition function that we see here in green, this is just the expectation of the predictive variance after having seen the gradient, after having seen one additional point. And because all of this is normally distributed, the predictive variance that we want to know about doesn't actually depend on the outcome of the experiment, just depends on the location of the experiment. Meaning, we can compute this acquisition function, again, in closed form very efficiently, and then we can optimize this. And if you look at this in this simple example, I mean, the outcome is what you would expect. It is that in order to reduce the uncertainty of the gradient, you need to sample a little bit to the left and a little bit to the right of this point. But how far to the left and to the right? This basically depends on the noise level. So if you have a super noisy function, then you don't want to sample super close, because basically everything that you measure about the gradient is noise. And how smooth the function is, if the function is very smooth, you can go farther away. So you kind of need to find the optimal trade-off in order to reduce the uncertainty of the gradient in an optimal way. And this is exactly where the optimal trade-off is at the peak of this function. Okay, let's see the algorithm in action. So GIBO works in basically two phases. The first phase is learning about the gradient. And the second phase is then using the information that we have learned in order to do gradient update. And there we can use whatever we want to do. We can use gradient descent, we can use LM, whatever your favorite optimisms. Okay, so we start with the same setting. We have this acquisition function, we maximize it, we do the evaluation. Now we have seen data, our posterior model changes. And now, since I have already evaluated to the left, my acquisition function says, okay, now it's time to evaluate to the right. We do this, and then we know enough about the gradient to do an update step. We are certain enough about this, and we update our current policy. Now, I guess the interesting part starts, because now here we already have some data, and we can reuse this data for our gradients. And this is very different from other kind of gradient estimators, where you basically throw away all the data after every iteration. We have our global model of the function, and we keep using this model. And now, basically, all of the data points that I have influence where I should vary next in order to maximize the information I get about this new gradient. Yeah, we can let this algorithm run. No. Yeah. Sorry?
It's
Yeah.
That might be this case. Yeah, we're like in council, fucking.
Should we? I mean,
It's fine, yeah, okay, next time I think it, yeah, it could be, I think it's more like, I think it's better you share, not share this video. Yeah, it's fine.
okay. Um, so we let the algorithm run, and it will, then move towards this local domain. And of course, you see, if I would have started the algorithm somewhere else, maybe over here, you would have picked randomly. No? So we really lose kind of the global exploration things that we have using BO. We just do gradient descent into the next local optimum. Okay, so how well does it work? Surprisingly well, I would say, for simple idea as this. No? So we compare this on a like in synthetic experiments. So the experiments that we have here are functions that are members of our HS or our kernel. So we kind of know that all of our model assumptions that we make with our process are actually true. And then we just ran the algorithm and compare this to an algorithm that is called augmented random search, which basically just does on-the-fly gradient estimates from zero information. We compare this also to just normal global Bayesian optimization and to like famous evolutionary search algorithm. And GIBO, the algorithm we propose here, is in red. And you can see that especially for higher dimensions, we really outperform all of these things. And not only in expectation, but you can also see kind of due to this active learning, actively reducing the uncertainty that we do this every time. So this plot contains like the standard deviation and the average of 40 runs, and you can see we basically have no variance for our results, whereas other algorithms do have quite a lot of variance. Which is nice because if you actually want to use an optimization algorithm in practice, you usually want to run it once. No? If you have an expensive problem, you want to optimize the controller of your quadcopter or whatever. Like you don't really care if you have slightly lower expected value on your costs. But what you really want is, okay, I'll let this run once, and I'm certain that now it works better than before. And this works quite well. Okay, so I guess it's time for a video. So we also tried this in practice. There is a small extension here though. So we have this kind of task the robot should learn. So this robot arm is balancing a pole. Super exciting, I know. And the goal of this task is that the robot arm should make the tip of the pole follow this trajectory. No, so the robot already knows how to balance the pole, but now it basically has to learn kind of force profile over time in order to make the tip follow this trajectory as closely as possible. And that is not, I mean, it's not super difficult task, but it's also, I mean, for me, it was trying this in the lab, doing it myself, is also not super easy. So balancing a stick, that's possible, but then moving the stick in a very precise way through space, that's actually not super easy, at least not for me. Okay, so it's time for video. So you can see here the lower arm is balancing the pole with a lot of black, I guess. Yeah, let's get the setup. So here, the idea is that we have two information sources. We have our robot running, like doing the task, but we also have a simulator. And now we want to combine both of these sources of information, and our algorithm should basically decide on its own, do I need like the expensive real world evaluation, or is it enough to evaluate my policy in this simulation? And the idea is here that the simulator is biased. No? It's not quite accurate. There are some effects that are not modeled in simulation, mainly kind of friction stuff. And yeah, so basically the algorithm decides, in order to improve my policy, do I need expensive but low bias information, or is it enough to grow this? So let's go through this a little bit. So here you will see now the progress of learning this task. So we start, so this is bird's eye view on this problem. So we see the robot from the top. Here is the tip, and the desired trajectory is this white dashed line. And so I show you the iteration. Iteration basically means the performance of policy after the gradient step. And depending on kind of where we are in the state space and how shallow our gradients are, I need more or less samples from the robot in order to estimate this gradient. So we see slight progress in learning this task. So iteration 0, we initialize everything to 0, robot is not moving, then starts to learn how to move and does kind of fast progress through all of these iterations. I let this now run for a bit, so you see it gets better and better at this task. And after 12 iterations, we stop the optimization because we were happy with the results. And so you can see the tracking is not perfect, but the error is also not so bad. So we have kind of an average error of 6 millimeters per second. And by the way, so this we never achieved with learning just in simulation. To have this kind of tracking error, you need data from the root system. Otherwise, like at least our simulator wasn't good enough. So the bias was too high. So learning this was possible with a total interaction time of 1 hour with the robot. So of course, the total time learning takes longer, because there is simulations happening always, but basically data from the robot is just 1 hour, which corresponds to 188 times rolling out once. Okay. So this was our video. So to summarize, these kind of Bayesian gradient estimates allow us to optimize noisy black box functions in a data efficient manner. If we have additional information sources, such as a simulator in robotics, it's really beneficial to include this. We can significantly decrease the kind of samples that we need from the grid system. Yeah, so also maybe what is nice, so since we published this, the algorithm in 2021, there have been, also like follow-up works that improve upon this algorithm and also have some, analysis, some theoretical analysis of the algorithm in other groups. Okay, that's it for GIBO. I will now switch. Almost. So if you want to try out, of course, the algorithm is available for users, and also will be an implementation hopefully soon. Okay, so now we switch gears a little bit. We leave the world of Bayesian optimization and do experience transfer. I guess that's a word that is. I don't need to explain what this is here. So the idea is that we want to use data that we collect in one system to use that. So the core motivation here is that I have what we call an offline scenario data set, meaning I have collected trajectories from n different robots, in this case quadcopters. The robots, of course, can't be super different. No, they need to be kind of similar, and I will precisely say what I mean by similar in a second. But the goal is, using this data, I want to design a controller that works on the n+1st robot. So a robot I have not seen, but this robot is similar to this robot. And because I don't know what this robot will be, it might be also one of these robots, so the controller should work on all of these robots and potentially other robots that are similar. And working here means it should stabilize the system. No? I mean, there is results on this kind of transfer might not be good for performance. Or if you want to optimize performance, that's not what you should do. Here we really are interested only getting a stabilizer. So why is this useful? Imagine I have a box of quadcopters, and all of them are slightly different. And I pull out one of these. I'm not going to do some learning-based control of this, but a lot of times learning-based control does require you to have kind of an initial stabilizing control. And this might be one way of how to get an initial stabilizing controller without ever collecting data on this one. Of course, we need data from all of these. Okay, so what do we mean by similar robots? So we here define kind of a robot fleet, which is what we mean. So this is all happening in the linear systems world. So we are saying a fleet of robots is a set of unknown linear systems. And the thing that these systems have in common is that they are all sampled from the same distribution. And they're sampled IID, meaning I have my box, with all quadcopters, and the n robots I pick are just random samples. So then we also assume there is some noise when we collect the data. And in order to kind of make any progress in identifying what system this is, we have to put some assumptions on this noise. And this is the assumption that we have here. It's a little bit technical, but basically the idea is that the noise trajectory should be just in the set that is defined by this LMI. And just to give you some intuition on this, we can parameterize this LMI in a way that basically we have a bound on like every single sample from this process noise. So this means I have some kind of limited energy that gets put into the system from the outside. And it also makes sense that we need something like this, because if there is kind of infinite energy that gets put into my system from an external disturbance, I guess identifying the system will be very hard. Okay. So we organize our data in a certain way. We put our trajectories in these matrices, and they're sometimes called Henkel matrices. But basically, the idea is that we have our state trajectory here, and since we have I different systems, we put this like we have n of these matrices. Then we shift the data by 1 for this other matrix, and we also have our input shift. Once we have kind of this data and our assumption on noise, we can now define an uncertainty set. And an uncertainty set are basically all systems that are consistent with my noise assumptions and the data. Meaning, when I see this data and I did not measure the noise, I basically, with finite data, I can't identify the one system that has created this data. But I can create a bounded set of systems, and all of these systems might be responsible for creating this. Okay, again, based on this, I now have n of these uncertainty sets, and now I want to combine this in order to get a nice control. So just to restate the goal is that I want a single state feedback controller, and this controller should stabilize a sample from my fleet with a certain probability. And this probability should be bigger than 1 minus alpha. And what I want from such a method that creates such a controller is that I can basically pick a level alpha. I'm saying, okay, I'm fine with 0 to 1% of my systems not being stabilized. But what I get from this is that I get to work with finite amount of data. So now to put all of this together into a nice picture to build some intuition, maybe all of this notation might be time. So the idea is that for this number, I have a one-dimensional system. I have my B matrix and my A matrix. And now the domain of my fleet, which is basically the set of all possible systems that are in my fleet, I indicate this here by this dashed blue line. Of course, I don't know this. No? If I knew, I would be done. I could just do robust control, stabilize the set, and done. Okay. What I have instead is I have these different trajectories and the uncertainty sets that I get from these trajectories. And these are these blue blobs here. No? So in this example, I have sampled 4 systems, and from these systems, I get these uncertainty sets. And now I can put the union of these sets into my robust control synthesis problem and basically tell us, please stabilize the union of these sets. Now, the result might be a controller like this here in green. So this is the set of all systems that are stabilized by a single controller K. And as we wanted, the blue blobs all inside the green regions. So yes, we can now stabilize all of the systems that we have seen, including their uncertainty sets. Now, you see the problem. The problem is that there is some part of the field which is not stabilized. No, and this is basically the alpha. No, so I now have a probability distribution over the set, and I'm saying that this white region here that is inside my fleet domain should have at most probability mass alpha. And yeah, so the key question is how many of these blue, like how many systems do I need in order to guarantee that this actually happens? So this is the main result of this paper. So I'm not going into like, yeah, just ignore most of the LMI. So basically when we solve this LMI, okay, maybe don't ignore it. So the LMI, as you can see, only contains the data. No, so there's no system identification step, whatever. So this is what we call direct data-driven control. No, so we write an optimization problem. We put here in our noise assumption, we put in the data, we give this to an LMI solver, and like half a second later, it will give us a solution to this problem. And this will be a controller that stabilizes all of the systems that I've measured from. And then this theorem tells us that if we are willing, like we fix alpha, and we also have to fix kind of a confidence parameter. And then if we have at least n systems where n is bigger than this formula, then the probability of a new sample being stabilized is actually alpha. So this is exactly what we wanted. No, we can now either, okay, I have 4 systems. So what is I can now compute the probability of the 5th system that I haven't seen being stabilized by the sync controller that stabilizes the initial 4. I can plug in like all of the numbers here. I rearrange this formula and I compute the probability. Or the other way around, I want a certain level of probabilistic robustness, and then I can compute how much data do I need. Okay. So we did a little bit of parameter study. I'm not for sure if I should go into a lot of detail on this. Basically, the takeaway message is, okay, empirically, our theory pans out. No? So if I have that much data, I'm basically guaranteed to be stable. But this parameter study also reveals kind of conservatism. So our bound tells us that we, in order to stabilize this synthetic example, we need at least 980 systems. But you can see, so green, basically the green means I have almost 100% stabilization. And you can see all of the circles turning green really a lot before. So basically after 32 systems, I'm already certain that all of my systems, at least in this example, will be stabilized. Yeah, so the nice thing about this, it does work as advertised, but it usually suggests maybe too high a number of systems that we should need. I think what you can also see on this plot is that if you want to stabilize a fleet of systems where we have some variations, then just taking a single example and creating a stabilizing controller for this is not enough. No, because you can see here for a number of systems 1, 2, or even 4. No, we see all of these circles are not green, meaning it doesn't work. So you really need multiple systems to stabilize this. So we not only did this on like synthetic linear systems, but we also tried this on simulated quadcopters. We used the GIBO in the drone environment to simulate drones. We kind of created variations by having them carry different payloads and generated data from here, from the simulation, and then tried out if the quadcopters could fly with our controller given a new set of payloads. And you can see here, so the task for the drone is to fly from the lower left to the upper right. And these colored lines are all different variations of the quadcopter. And you can see that they first of all manage to complete their task. And even if there is a small wind gust that blows them away from the trajectory, then they are still able to do this. If you do it the naive way, which we did by kind of putting all the data that we have into a standard SysID algorithm that like is just a square, and then doing some Rohr controller synthesis on this, then this won't work. No? So if you just do it the naive way, then yeah, all of the quadcopters crash. But this is the crash you can see. Okay, so we are sadly there is no video on this because we are having a lot of problems with our hardware test bed. So they do fly sometimes, but we have not. Yeah, so our problem is mainly kind of delay and jitter in the control commands, and this really. So because in order to achieve kind of this level of robustness, the controllers need to be like a little bit more on the aggressive side. But if you then have kind of unexpected delays in your command updates, then yeah, things crash. So if we have a good day, they fly. If we have a bad day, they don't. Yeah, so no video on this. Okay, so last slide to summarize. This method allows us to have robust control design obtained from relatively small data sets, but we collect this data set on multiple systems, and we are able to stabilize unseen systems that are belonging to the same fleet. We get probabilistic stability guarantees for these unseen systems. And it does work quite well in the simulation environment. Yeah, but we are having significant problems getting this one out there. So kind of this work really is based on results from scenario optimization by Campi and colleagues, and most of the LMI controller synthesis, direct data-driven control stuff is heavily based on the work by Van Baarle and colleagues. Okay, so being slightly over time, I'm done with the presentation.